All right, so we're in section 2.4, and we're going to talk about complex numbers. So I know you're familiar with imaginary numbers, complex numbers to a certain extent already. So what we're doing again is going to be a little bit of a review, but complex there are a lot of very, very simple equations that come up that we can't solve with real numbers. One of the most simple, x squared plus 1 equals 0. We can't solve that with real numbers. Pretty simple equation, pretty simple polynomial. Because if we try to solve this, we end up with x squared equals negative 1 and x equals the square root of negative 1. Well, we've always said for real numbers we can't take the square root of a negative number. So what mathematicians did was they said, okay, well let's call this thing the square root of negative 1. Let's call it I. And we call I the imaginary unit. It's unfortunate that they chose the word imaginary, because it gives the impression that it's not that it's something kind of artificial. So it doesn't really mean artificial. We've talked about real numbers, so now we have an imaginary numbers. Guys, let's close the computers, please. It just means that it's something outside the real numbers. That's what we mean by imaginary. I've had students say, "Oh, we're going to talk about those fake numbers again." So it's not really that they're fake, just that they're not real numbers. And so we have this. I has this special property that I squared equals negative 1. So this is how we define our imaginary unit. There isn't any other number that we know of that has this property, so we say let's define one. Let's make this number up. And then what we do in mathematics is say we're going to make this thing, and we'll see what happens. What happens when we start working with this thing. That's part of what we do in mathematics. It's not always often it's to solve a particular problem, but sometimes it's just let's look at this thing and see what comes out of it. The thing that I find interesting about I and the imaginary unit is it actually didn't originally come from trying to solve this equation. This is a pretty simple equation. It actually, the idea of I came from trying to develop a formula for solving cubic equations. So trying to come up with something like the quadratic formula for cubic equations. Well, it turns out that in this formula, it's a pretty complicated formula, even for cubic equations that have all real solutions, in the formula you end up taking the square roots of negative numbers. So in order to use a formula to solve an equation that has all real solutions, you end up taking the square roots of negative numbers. So that's originally where it came from, was developing this formula for cubic equations. So I think that's kind of interesting that it originally didn't come from a simple equation like this. It came from trying to find this solutions to cubic equations. So we have this imaginary unit. So I is the square root of negative 1. We combine it with real numbers to come up with complex numbers. And complex numbers are numbers that we can write a plus bi, and we call this standard form. And when we write them in standard form, a and b are both real numbers. So that's our standard form for a complex number. And we also need to remember that real numbers are inside, they're a smaller set than complex numbers. So if I draw a Venn diagram, the complex numbers are out here, and real numbers are inside the complex numbers. So real numbers are complex numbers. The real numbers are just complex numbers where we don't have this part. We call this part the real part, and we call this part the imaginary part. So real numbers are just complex numbers where the imaginary part is 0. And if we have a complex number where the real part is 0, we call it a pure imaginary number. So there's no real part. So that's just what we mean by a complex number: real part, imaginary part, standard form. So what we want to talk about today are just the basic operations with complex numbers. We're going to add them, subtract them, multiply them, and divide them, and just remind ourselves of the rules for that. That's really all we're doing. So first thing we want to know is, when are two complex numbers equal? So we're going to talk about equality. So if I have a plus bi, and we know that equals c plus di. If these are equal, what do you think that's telling us? When do we think, what's going to make sense for complex numbers to be equal? Right, the real parts have to be equal and the imaginary parts have to be equal. A and C are equal and B equals D. So the real parts have to be equal, the imaginary parts have to be equal for them to be equal. Addition and subtraction. So if we want to add or subtract two real numbers, so let's say a plus bi plus c plus di, how are we going to add these? What do we do when we add these? What's going to be the real part of the answer? A plus c. A plus c is my real part. And what's going to be the imaginary part, the part that goes here with the... And I'm just going to leave the I outs here, so just b plus d. So we add the real parts and we add the imaginary parts. I think of it like polynomials. We're adding like terms. The real parts are like terms and the imaginary parts are like terms. So they add like polynomials. So that's, I think of it as like polynomials. And then the thing to remember, where students often make mistakes with subtraction, is if we have a plus bi and we're subtracting c plus di, we need to remember to subtract this entire quantity. A lot of times, if we have it written like this, we forget that we're subtracting the d part also. So this is a minus c plus b minus d I. So we're distributing the minus. So if I do a quick example, if I have 3 plus 5i minus 8 plus 7i, I need to remember I'm subtracting that entire quantity. So we have a 3 minus 8, we get a negative 5, and a 5 minus 7, negative 2i. We have to remember that goes, the negative sign, the subtraction goes for the entire quantity for the second part. That's where most people make mistakes on subtraction. But again, it's just like polynomials. So we all good with that? Nothing too earth-shattering here. All right, let's talk about multiplication. So I just want to do, for multiplication, I'm just going to do a few examples. If we had 5 plus 3i, and we're multiplying that by 2i, how are we going to do this problem? Distribute. So we're going to distribute just like we do with polynomials, just like we do with any other number. So this is 10i, I'm going to write out the entire step, plus 6i squared. And 6i squared is negative 1 times 6, or negative 6. So we get, in standard form, negative 6 plus 10i. So we can distribute. Turns out that the various things that we can do with real numbers, we can also do with imaginary numbers. Distributive property, commutative property, associative property, all of those things work as long as we remember when we're adding and subtracting, we add and subtract the real parts and the imaginary parts. So what if we had, rather than just multiplying by a single number, what if we had 5 plus 3i, and we're multiplying that by 2 minus 4i? What are we going to do here? Distribute. And if it helps you remember, our shortcut when we multiply polynomials, you can think of foiling. We FOIL this. So we're just distributing, just like we did with the 2i. We're just doing it with a quantity. So let's multiply this out. So I get, and I usually have to write out the steps, or I make a sign error or arithmetic error somewhere. So I get a 10 minus 20i plus 6i, and then a minus 12i squared. So then now we combine like terms. So I get, combine the real part and the imaginary part. I get a minus 14i, and I squared is negative 1. So negative 1 times negative 12 is plus 12. Finally write it in standard form, so I get 22 minus 14i. In standard form. So multiplication is like polynomials, also we distribute. Now we need to talk about division. We have our three of our major operations talking about division, but there's one thing we need to know about before we do division. Any questions before we go on? We all good on this? Complex conjugate. To find the complex conjugate, we change the sign on the imaginary part. That's all we have to do. So what would be the complex conjugate of negative 3i? 3i. How about negative 5 plus 2i? Negative 5, oops, not an 8. Negative 5 minus 2i. Just change the sign on the imaginary part. What would be the complex conjugate of 10? 10. There's no imaginary part there. So we change the sign on the imaginary part. What happens when we multiply a complex number by its conjugate? What do we get? What happens? Do you remember? The i's go away, and we just end up with a real number. So when we multiply a complex number by its conjugate, we end up with a real number. And that's what we're going to use when we talk about division. And later on, we'll do a little bit more work with complex numbers, and multiplying a complex number by its conjugate will tell us another thing about our complex number. But for now, we're just going to use it for division. So now we know about our conjugate. We can talk about doing division with complex numbers. So to divide two complex numbers, we multiply the numerator and denominator by the conjugate of the denominator. And the stuff that we're doing today is pretty mechanical. It's not particularly exciting, but we just and we're just reviewing our ideas, reviewing our operations, so that later on we can do some more interesting things with complex numbers. So I just want to do a couple of examples with division. So if we have 3 plus 5i, and we're dividing by 2i. So I'm going to multiply the numerator and denominator by the conjugate of the denominator. So I multiply by negative 2i in the numerator and the denominator. And then I just simplify. I do the operation and I simplify. So if we write this out, this gives me, what do I get here? Minus 6i minus 10i squared. And in the denominator we get minus 4i squared. And now we simplify. I don't want to start canceling i's here. I'm just going to simplify. So I get a 10i squared is negative 1, so I get 10 minus 6i divided by I squared is negative 1, so divided by 4. Can I simplify this? So what does this simplify to? I can write it as 5 minus 3i over 2, and technically, to be in standard form, I don't mind if you write it like this. If technically to be in standard form, this would be 5 halves minus 3 halves I. I'm fine with this. Technically, this is standard form. So there's one division problem. Let's do one more where we have a quantity here. So let's do 2 minus 4i, and we're dividing by 3 plus 2i. So we multiply the numerator and denominator by our conjugate, and then simplify. So I multiply by 3 minus 2i over 3 minus 2i. So when I do this, what do I get in the numerator? All right, everybody good with that? And in the denominator, what do we get? Okay, and we see that our 6 minus 6i plus 6i, they cancel. I squared is negative 1. So we can simplify. So the numerator, how do we simplify the numerator? What does it simplify to?
Negative 2 minus 16i over 13 minus 13.
Over 13. So I would be fine if you wrote the answer this way. In standard form, this would be negative 2 thirteenths minus 16 thirteenths I. Lee's the champion at imaginary math. All right. So questions on division. Multiply numerator and denominator by the complex conjugate. All right, one last thing to talk about is taking the square roots of not just -1, but the square roots of negative numbers. And we get, this is what we call the principal square root. And the reason we need to talk about this is we can run into a situation where there could be a little bit of ambiguity, where we're not 100% sure what we want to do. So we're going to define, we'll make this our definition, so we always do it at the same time, the square root of -a, where a is a real number. As I times the square root of a. We're making this our definition. This is how we take the square root of a negative real number. It's I times the square root of the number. And we call this the principal square root. The reason that we make this our definition is we can run into a situation like this. Square root of -5 times the square root of -5. Well, if we follow our normal rules for square roots, we can say this is the square root of -5 times -5. Well, -5 times -5 is positive 25, and that equals 5. We don't want to do this. We want to use our definition and say this is I times the square root of 5 times I times the square root of 5, which is I squared times the square root of 25, which is -5. So whenever we take the square root of a negative real number, we want to use this principal square root. We want to use this definition. Because if we don't use the definition, one person could do it this way and say, well, this is right. Another person could say, well, no, the square root of -1 is I, so I take that out and I do it this way. And so we want to make sure that we're always doing it the same way every time. And it turns out that using this definition, the principal square root definition, makes other things work out the way we want them to with complex numbers. So just remember that this is how we define our square root of a negative real number. All right, any questions on those operations? Okay. I wanted to talk quickly about, I know this square roots, complex numbers, nothing extremely exciting. Yes? Yes. It's a little bit dry. It's not that exciting. And actually doing synthetic division and finding zeros, really not that exciting. But these ideas can lead to some really interesting math. And that's what I wanted to talk about just for a minute. This is nothing that's going to be tested. Nothing that I'm going to ask you questions about. This is an idea that I found out about when I was I don't know, a sophomore, junior in high school. This is what really got me interested in that. Have any of you ever heard of the Mandelbrot set? If I show you a picture, you'll probably recognize it. Grab this. There we go. There's the Mandelbrot set. So Mandelbrot set is probably one of the most famous fractals ever, and it shows up in a lot of different places. What's really cool about the Mandelbrot set? A couple of things. If you look at the shape here, and the shape here, you see that it is repeated in smaller copies kind of around the edge of the shape. And the same thing here, so we get smaller copies, and we get a smaller copy out here. Turns out that if you zoom in to these places, this happens over and over and over again. You get these smaller copies. Way, way, way down inside here, there's smaller copies of the bigger set. So the way the Mandelbrot set works, the way it comes about, is with complex numbers. So what we do with the Mandelbrot set is the Mandelbrot set is a function where we plug in complex numbers. So z is a complex number. We pick a point in what we call the complex plane. So instead of the y-axis, we have the imaginary axis, and we call the x-axis the real axis. So a number like 3 plus 2i would be over 3 and up 2. So that would be a point in the imaginary plane, 3 plus 2i. What we do is we take a point in the complex plane and we plug it into this function. We square the number and we add a constant to it. C is just a constant. We take whatever we get out, plug it back into the function again. Square it, add a constant to it. Whatever that answer is, we plug it back in again. You keep doing that over and over and over. Every time you get an answer, you plug it back in. Well, the points in the complex plane, let me go back to the picture here. The points in the complex plane where after we do that, plug that in over and over and over again, basically as many times as we want, and the number never gets infinitely large, are the points that we color black. So we call those points inside the Mandelbrot set. We can do that process over and over and over again, and they never go to infinity. And so we get all this interesting shape. It's all connected. These little tendrils are all connected by points that are inside the set. The colors come from the numbers that we plug in the complex plane. I think, if I remember correctly, the Mandelbrot set, the axis is over here somewhere, right around here. The colors come from plugging numbers into that function z squared plus c and deciding how fast those numbers get infinitely large. So if we if we go through the process 1,000 times, we're going to color those points, all of those points that take 1,000 times before the numbers get really, really, really large. We'll color those points blue. And if it takes 10,000 times, then we'll color those points some other color. And if it takes 100,000 times, then we'll color those points another color. So that's where all the colors come from. So you get these patterns in these numbers from plugging it into a very simple complex function, and then just seeing how quickly the points go to infinity. And it turns out that this detail along the edge and the smaller pieces are reproduced no matter how much we zoom in. So if we zoom in on a tiny little section of the complex plane and do that process in that tiny little section, you get something similar. You can zoom in even further and look at an even tinier section, and the detail's still there. So I found a video that shows that. That's pretty cool. So I want to show you the first part of this video. So this shows a zoom down in the corner. Can you give me the video? There we go. Play. There we go. So down in the corner you see a zoom into you should see it worked earlier. There we go. Maybe it doesn't like full screen. So down in the corner is we're zooming into a smaller section of the complex plane. So somewhere in here, and we're just zooming into a smaller and smaller and smaller piece of the complex plane, doing that same process that I talked about with the z squared plus c, coloring the points depending on how quickly they go to infinity. We can keep zooming in. So by now we're in just a tiny, tiny, tiny little piece of the complex plane. and you get all these crazy patterns generated by this z squared plus c function. And then that was as far as the computer could do it. So, Mandelbrot set one example of something I find really fascinating that have to do with complex numbers. There's lots of other things about complex numbers that turn into some really interesting things. Probably the most fascinating class that I took when I was in college, a fascinating math class, was complex variables. Just a really different kind of math and a different way of working with things. So if you ever get a chance to decide to go into math, take complex numbers, complex variables, or complex analysis, it's really, it was the most interesting math class that I took. All right, homework. Looks like a lot, but most of it is very, very easy. We're just doing these operations with complex numbers. And the reason I picked all these separate numbers is because I didn't want you guys doing like 10 different things where you're adding complex numbers. I wanted you to do just a variety of things. There you go. And then the other classes, they